What if everything you know about star size is wrong? Tonight, we're going to explore the true scale of Betelgeuse. You've probably seen that reddish dot in Orion's shoulder thousands of times, but here's what most people don't realize. Betelgeuse isn't just big, it's so monumentally huge that if placed at our solar system's center, it would engulf Earth, Mars, and reach beyond Jupiter. By the end of this journey, you're going to see our universe in a completely different light. Before we dive in, if you enjoy these cosmic explorations, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a real difference for me. Get comfortable. This is going to be incredible. You've probably seen that reddish dot in Orion's shoulder thousands of times. Maybe you've pointed it out to friends during winter evenings, or noticed it twinkling through your bedroom window. But here's what most people don't realize about that familiar orange-red point of light. Betelgeuse isn't just big, it's so monumentally huge that everything you think you know about size is about to change forever. Tonight, we're going to take a journey that starts with this star you recognize and ends somewhere so vast that human language begins to fail. By the time we're finished, you're going to see our universe in a completely different light. And you might never look at the night sky the same way again. Let's start with what you can see. Right now, if you step outside on a clear winter night, you'll find Orion hanging in the sky like a cosmic giant. There's Betelgeuse, marking the hunter's left shoulder, glowing with that distinctive reddish color that's caught human attention for thousands of years. Millions of people around the world identify this star easily. It's one of the brightest points in our night sky. Impossible to miss once you know where to look. But here's the first thing that should make you pause. If our sun were a standard 60-watt light bulb, Betelgeuse would be like the massive floodlight illuminating an entire stadium. What makes this even more remarkable is that we're watching Betelgeuse change before our very eyes. Ancient Greek astronomers, including Ptolemy, described this star as yellowish in their careful observations. Today, we see it as distinctly red. Think about that for a moment. Like a person aging and their hair gradually changing color, Betelgeuse is evolving on a timescale we can actually observe. This transformation reveals a cosmic process happening at breakneck speed by stellar standards. Now let me give you some numbers, and I'll do my best to translate them into something your brain can actually process. Betelgeuse contains enough mass to equal 548,000 planet Earths stacked together. But here's a better way to think about it. The light you're seeing from Betelgeuse tonight actually left that star 700 years ago, when that light began its journey toward your eyes. Dante was writing the Divine Comedy, and most of Europe still believed the Earth was flat. If you could somehow travel to Betelgeuse at the speed of a commercial jet, let's say you're cruising at a comfortable 900 kilometers per hour, your journey would take 870 million years. That's longer than complex life has existed on Earth, but the size is where things get truly mind-bending. Betelgeuse has a diameter roughly 700 times larger than our Sun. I know that number probably just bounced off your brain without making much impact. So let me put it this way. If our Sun were a ping-pong ball, Betelgeuse would be a basketball sitting next to it. Actually, let me try something even more dramatic. If we could somehow replace our Sun with Betelgeuse, and I'm glad we can't, the surface of this red giant would extend far beyond the orbit of Jupiter, Mercury, Venus, Earth, and Mars would simply vanish, swallowed up inside this stellar monster like pebbles dropped into an enormous lake. We'd be orbiting inside the star itself if we could somehow survive the experience. Here's where Betelgeuse gets paradoxical in a way that perfectly demonstrates how the universe loves to confound our expectations. Despite being absolutely gigantic, Betelgeuse is actually cooler than our Sun by about 1/600 degrees Celsius. It's like a massive campfire that burns with a lower flame temperature than a smaller fire, but compensates by being so enormous that it still produces incredible heat. How enormous? Betelgeuse shines with the brightness of 126,000 suns combined. Think about that. If you could line up 126,000 copies of our sun and somehow make them all shine simultaneously, that's how much light Betelgeuse pumps out every single second. And here's something that might surprise you. Betelgeuse is actually a baby by cosmic standards. At only 10 million years old, it's incredibly young. If the entire 4.5 billion year history of Earth were compressed into a single year, Betelgeuse would have been born just 2 days ago. But because it's so massive, it's like a racing car engine running in the red zone constantly. While our sun will live for about 10 billion years total, Betelgeuse will burn through all its nuclear fuel in just a few million more years. This is a star living fast and dying young on a cosmic scale. You might remember the excitement that rippled through the astronomy world between 2019 and 2020, when Betelgeuse suddenly dimmed by 60% of its normal brightness. For months, it became noticeably fainter in the night sky, dim enough that even casual stargazers noticed the change. Scientists around the world wondered, was this the beginning of the end? Was Betelgeuse about to explode? The speculation was understandable. Like a light bulb flickering before it burns out, this dramatic dimming seemed to signal that something major was happening. The Hubble Space Telescope eventually solved the mystery. Betelgeuse had ejected a massive blob of material equivalent to the mass of our entire moon, which had cooled and formed a dust cloud that temporarily blocked our view of the star. But this event revealed something crucial about Betelgeuse's nature. It's profoundly unstable. Betelgeuse doesn't just sit there burning steadily like our sun. Instead, it pulses like a gigantic cosmic heart, expanding and contracting in regular cycles that last about 420 days. During these pulsations, the star literally grows and shrinks by distances equivalent to the gap between the Sun and Mars. Imagine a balloon the size of Jupiter's orbit inflating and deflating rhythmically. Every time Betelgeuse inhales, it moves enough material to form thousands of Earth-sized planets. Every time it exhales, that same material rushes back toward the core. This breathing motion is so violent that it creates shock waves that ripple through the star's atmosphere. This instability points to something both terrifying and wonderful. Betelgeuse is a supernova waiting to happen. Astronomers estimate it will explode sometime in the next 100,000 years, which is essentially tomorrow in cosmic terms. When Betelgeuse goes supernova, it will be spectacular beyond imagination. For about 3 months, it will shine as brightly as the full moon. Visible even in broad daylight, the explosion will be 10 billion times brighter than the star is today. From our perspective, it will be like having a second sun in the sky, casting shadows at midnight. But here's the beautiful part. That explosion will forge and scatter heavy elements throughout space. The iron in your blood, the calcium in your bones, the oxygen you're breathing right now. All of these elements were created in the nuclear furnaces of stars like Betelgeuse. Right now, in the core of Betelgeuse, temperatures reach 3 billion degrees Celsius. At those temperatures, nuclear fusion creates carbon, oxygen, silicon, and iron through processes so energetic they're impossible to replicate on Earth. Betelgeuse is essentially a cosmic factory, running 24 hours a day, producing enough iron each year to equal the mass of 10 million planets like Earth. This stellar factory doesn't keep its products to itself. Betelgeuse constantly sheds material through powerful stellar winds that race away from the star at 30 kilometers per second. Every 6 years, these winds carry away material equivalent to the entire mass of Earth. Over millennia, this creates a bubble of hot gas surrounding the star that stretches 4 light-years across, larger than the distance to our nearest stellar neighbor. Betelgeuse is also a cosmic wanderer. It's racing through space at 30 kilometers per second, creating a bow shock wave as it plows through the interstellar medium, like a speedboat cutting through water and leaving a wake behind it. Betelgeuse creates a trail of heated material that stretches for light years. In 1,000,000 years, this stellar nomad will be in a completely different region of our galaxy. Modern astronomy has given us the ability to study Betelgeuse in extraordinary detail. Using interferometry, essentially combining multiple telescopes to create a virtual telescope the size of a continent, astronomers can observe features on Betelgeuse's surface equivalent to distinguishing a coin on the moon. The Hubble Space Telescope has revealed hotspots and cool regions across its surface, showing us a turbulent stellar atmosphere with convection cells as large as our inner solar system. Here's something that perfectly captures how alien these giant stars are, despite containing the mass of 15 suns. Betelgeuse has an average density lower than the air you're breathing right now. It's like cosmic cotton candy, enormous in volume but incredibly tenuous. If you could somehow compress Betelgeuse to the density of our Sun, it would shrink to only 15 times the Sun's diameter. The discovery of Betelgeuse's true size in 1920 by Michelson and Pease was a pivotal moment in astronomy. For the first time, humans could directly measure the diameter of a star other than the Sun. And what they found revolutionized our understanding of stellar diversity. Like Galileo's discovery of Jupiter's moons, this observation shattered our assumptions about the universe and revealed that stars come in varieties we never imagined. Let me leave you with some mathematics that might make your head spin. If Betelgeuse were hollow, it could contain 343 million copies of our Sun. The total energy it produces equals 2.8 trillion hydrogen bombs exploding every single second. To match the energy output of just 1 second of Betelgeuse's existence, all of humanity would need to work at our current rate of energy consumption for 500,000 years. But here's the thing that should really capture your imagination. Despite all of this incredible grandeur, despite being large enough to swallow Jupiter's orbit, despite outshining 126,000 suns, Betelgeuse is just the beginning. It represents merely the first step on a cosmic ladder of sizes that will challenge everything you think you understand about scale. There are stars out there that make Betelgeuse look as small as our Sun appears next to Betelgeuse itself. Our cosmic journey is just beginning. But before we venture into those truly mind-bending scales, let's take a moment to put Betelgeuse in context by meeting some of its stellar neighbors. You see, the night sky is full of giants, and comparing them reveals just how diverse and spectacular stellar evolution can be. Look back at Orion for a moment. There, marking the hunter's foot, shines another supergiant that perfectly demonstrates this diversity. Rigel burns with brilliant blue-white light, and if Betelgeuse is like a massive campfire, then Rigel is like an industrial blowtorch. Despite being smaller than Betelgeuse in diameter, Rigel packs 79 times the mass of our Sun and burns with a surface temperature of 12,000 degrees Celsius, hot enough to make Betelgeuse seem relatively cool by comparison. The energy output is staggering. Rigel shines 40,000 times brighter than our Sun, compared to Betelgeuse's 126. Solar luminosities. But here's what's fascinating. Rigel achieves this incredible brightness through pure temperature rather than size. It's like comparing a small, white-hot welding torch to a massive, cooler bonfire. Both produce enormous amounts of light, but through completely different mechanisms. Travel south in your imagination to the constellation Scorpius, and you'll find Antares, whose very name means rival of Mars because of its similar reddish color. At 680 times the diameter of our Sun, Antares is slightly smaller than Betelgeuse, but in many ways they're like twin sisters separated by hundreds of light years. Both are red supergiants in the final stages of their stellar lives. Both pulse and vary in brightness, and both are destined to explode as supernovas in the cosmic near future. But here's where things get interesting. When astronomers study these stellar giants, they discover that size doesn't always correlate with what you might expect. Consider Aldebaran, the orange star that marks the eye of Taurus the bull. At only 45 times the Sun's diameter, Aldebaran seems almost modest compared to Betelgeuse, like a ping-pong ball next to a basketball. But remember, even this small giant is still 150 times larger than our Sun. It's a perfect reminder that in the world of stellar giants, our sense of scale becomes completely warped. Then there's Arcturus in the constellation Betelgeuse, which demonstrates stellar efficiency at its finest, with only 26 times the Sun's radius and just 1.08 times its mass. Arcturus manages to shine 170 times brighter than our star. It's like a perfectly tuned engine that extracts maximum performance from minimum fuel, while Betelgeuse burns through its nuclear reserves like a gas-guzzling sports car. Arcturus represents stellar engineering at its most elegant. For a study in stellar stability, look to Pollux in Gemini, the brighter of the celestial twins. With a radius 9 times that of the Sun, Pollux has been shining steadily for 724 million years. If Betelgeuse represents a cosmic storm, Pollux is a gentle cosmic breeze. It's lived nearly 75 times longer than Betelgeuse has even existed, illustrating how different evolutionary paths lead to vastly different stellar lifespans. But some giants make even Betelgeuse look restrained. Betelgeuse, hidden in the northern constellation Cepheus, undergoes pulsations so extreme they dwarf Betelgeuse's own dramatic breathing. This star varies in radius between 1,050 and 1,900 times that of the Sun. Imagine a balloon that inflates and deflates by an amount greater than Saturn's orbit. During its cycles, Cepheus literally transforms from one type of stellar monster into an even larger one, making it one of the most dynamic objects in our galaxy. Deep in the same constellation lurks Cepheus, known to astronomers as the Garnet Star for its intense red color. This semi-regular variable can expand to 260 times the Sun's radius during its maximum phases, like a cosmic jewel embedded in the northern sky. Cepheus pulses with a period of about 2 years, breathing like some vast cosmic organism in deep slumber. These comparisons reveal something crucial about stellar classification. Astronomers distinguish between giants and supergiants, and the difference is profound. Red giants like Arcturus range from 10 to 100 times the Sun's radius, while supergiants like Betelgeuse exceed 200 solar radii. It's like the difference between hills and mountains. They might seem similar from a distance, but they represent fundamentally different categories of stellar evolution. Giants are typically lower-mass stars in relatively stable phases of their lives, gently fusing helium in their cores while maintaining relatively steady sizes. Supergiants, on the other hand, are massive stars burning fuel so rapidly that they're racing toward explosive endings. They represent stellar evolution in fast-forward, living brief but spectacular lives. The colors of these stellar giants tell their own story. Betelgeuse belongs to spectral class M, indicating surface temperatures between 2,400 and 3,700 Kelvin, like cosmic thermometers. Stellar colors reveal temperatures. The hottest blue stars exceed 30,000 Kelvin, while the coolest red stars fall below 3,700 Kelvin. Betelgeuse compensates for its relatively low temperature with sheer surface area. It's like heating a house with a massive but cool fireplace rather than a small but blazing furnace. Some of these stellar giants remain hidden from our naked eye view, concealed behind veils of their own creation. NML Cygni, lurking in the constellation Cygnus, reaches 650 times the Sun's radius, significantly larger than Betelgeuse. But this giant is so enshrouded in dust from its own stellar winds that it remains invisible in optical light. Only infrared astronomy revealed its true nature, showing us that many supergiants remain hidden behind the cosmic dust they continuously create. The discovery of such hidden giants has revolutionized our understanding of stellar populations. KW Sagittarii, positioned toward our galaxy's center at a distance of 6,200 light-years, stretches 1.9 times the Sun's radius. Like a distant lighthouse on a cosmic highway, it demonstrates that red supergiants are scattered throughout the Milky Way. Not confined to our local stellar neighborhood, these discoveries have also revealed something unexpected about stellar physics. Normal stars follow predictable relationships between mass and brightness. More massive stars shine proportionally brighter. But supergiants like Betelgeuse break these rules spectacularly. Despite having only 15 times the Sun's mass, Betelgeuse shines 126,000 times brighter. It's like athletes who somehow burn energy at rates far beyond what their body mass would predict. Even more remarkable are the red supergiants found in our galactic neighbors. WOH-G64, residing in the Large Magellanic Cloud, boasts a radius between 1,540 and 1,730 times that of the Sun. As an ambassador from another galaxy, this supergiant proves that the formation of extremely large stars isn't unique to the Milky Way. Its existence expands our understanding of stellar evolution in environments with different chemical compositions and gas densities. All these stellar giants operate near fundamental physical limits. There's something called the Eddington limit, a cosmic speed limit of sorts that determines how bright a star can become before its own radiation pressure overcomes gravity and blows the star apart. Betelgeuse operates dangerously close to this limit, which explains why it constantly sheds material through powerful stellar winds. Beyond the realm of supergiants lies an even more extreme category: hypergiants. Stars like Eta Carinae and P Cygni possess masses exceeding 100 times that of the Sun and luminosities millions of times greater. Like Formula One cars compared to regular vehicles, hypergiants represent the absolute extreme of stellar evolution. They're so unstable that they can explode as supernovas or collapse into black holes with little warning. The ultimate fate of these stellar giants depends entirely on their initial mass. Stars beginning life with 8 to 25 solar masses become red supergiants like Betelgeuse and eventually explode as Type II supernovas. More massive stars become blue hypergiants, while less massive ones never reach the supergiant phase at all. It's like different rivers flowing toward different oceans. The initial mass determines the entire evolutionary pathway. The instability we observe in these giants isn't accidental. It's a fundamental feature of this evolutionary phase. Nearly all red supergiants exhibit brightness variations, indicating internal stress as radiation pressure battles against gravitational collapse. Like patients with irregular heartbeats, these stellar giants show clear signs of the cosmic equivalent of cardiac distress. What makes some stars grow larger than others often comes down to metallicity, the abundance of elements heavier than hydrogen and helium. Like different ingredients in cosmic recipes, varying metallicities produce different stellar outcomes. Stars poor in heavy elements can grow larger before exploding, while metal-rich stars face stronger radiation pressure that limits their maximum growth. Many of these supergiants exist in binary systems, creating complex gravitational dances that affect both partners' evolution. These cosmic partnerships can accelerate mass loss, alter pulsation periods, or even synchronized supernova explosions. Betelgeuse itself may have a companion star that hasn't been definitively detected yet. But here's what should really capture your imagination. Comparing Betelgeuse to all these other stellar giants reveals that we've only sampled a tiny fraction of the universe's stellar diversity, like mountaineers who've reached base camp and can finally see the true peaks ahead. Our exploration of stellar giants has only just begun. There are stellar objects so large that they make even Betelgeuse appear diminutive, forcing us to expand our perspective about cosmic scales yet again. The giants we've explored tonight, impressive as they are, represent merely the foothills of a mountain range that reaches towards scales so vast they challenge the very limits of what physics allows to exist. Located 900 light-years away in the constellation Canis Major lurks VY Canis Majoris, our first glimpse of true stellar monstrosity. With a radius 420 times that of our Sun, this hypergigant makes even Betelgeuse look modest in comparison. To put this in perspective, if our Sun were a ping-pong ball, V Canis Majoris would be a spherical Olympic swimming pool. That's not a metaphor. I mean an actual swimming pool, complete with diving boards, wrapped into a perfect sphere. If we could somehow transplant VY Canis Majoris to the center of our solar system, its surface would extend far beyond Jupiter's orbit, reaching nearly to Saturn. Our entire planetary system would be swallowed whole, with room to spare. But VY Canis Majoris isn't content to simply exist as a stellar giant, it's also a cosmic artist. This star has created an intricate nebula from material it's ejected over thousands of years. Like a sculptor working with gas and dust instead of marble, VY Canis Majoris has crafted structures visible through telescopes that stretch for 10 light-years in every direction. The nebula contains the equivalent mass of 30 suns, spread into delicate formations of arcs, knots, and filaments that rival any earthly artwork in their complexity. Here's something that perfectly captures how alien these hypergigants are. Despite containing 30 times the mass of our Sun, VY Canis Majoris has an average density 5 to 10 times lower than the air you're breathing right now. It's like cosmic cotton candy, a gigantic cloud of hot plasma so tenuous that most of its volume is essentially empty space. An astronaut flying through its outer layers would experience conditions more rarefied than the best vacuum chambers we can create on Earth. This stellar monster is also remarkably violent. VY Canis Majoris undergoes explosive eruptions that can eject material equivalent to Earth's entire mass in just a matter of days. These cosmic volcanic eruptions create shock waves that race outward at hundreds of kilometers per second, temporarily altering the star's size and brightness for decades at a time. Imagine a mountain-sized bomb going off inside a star already larger than planetary orbits. That's the scale of instability we're dealing with. The star operates as a massive dust factory, annually producing enough microscopic particles to form an asteroid the size of Ceres. Like a cosmic industrial facility running around the clock, VY Canis Majoris converts hot gases into solid particles through complex processes involving condensation and crystallization. This dust will eventually spread throughout our galaxy, providing raw materials for future generations of stars and planets. For decades, the VY Canis Majoris remained hidden from our view, concealed behind veils of dust from its own stellar winds. Only when infrared astronomy matured could we peer through these cosmic curtains to reveal the true nature of this giant. It was like using thermal imaging to detect heat signatures through thick walls. Infrared light penetrated the dust clouds that completely obscured the star in visible wavelengths. This discovery revolutionized our understanding of stellar populations. Suddenly, astronomers realized that countless hypergigants might be lurking throughout our galaxy, Hidden behind the dust clouds they continuously create. VY Canis Majoris wasn't unique. It was the first member of a previously invisible population of stellar behemoths. The classification of VY Canis Majoris has sparked ongoing scientific debate. Is it an extreme red supergiant, or does it qualify as a true hypergiant, like a border between countries on ancient maps? This distinction reflects the limitations of our scientific categories. The star's properties place it precisely on the boundary between established classifications, forcing astronomers to refine definitions that were once considered settled science. Time is running short for this stellar giant. Estimates suggest VY Canis Majoris could explode as a supernova at any moment within the next 100,000 years. Essentially tomorrow in cosmic terms. Like a massive candle burning in its final moments before extinguishing, this star consumes nuclear fuel at a rate that guarantees a spectacular end in the cosmic near future. When it explodes, the supernova will be visible during daylight hours and will forge heavy elements essential for future life. When VY Canis Majoris was first accurately measured, it forced astrophysicists to completely revise their models of stellar physics. Like discovering that mountains could be much taller than anyone thought possible, this measurement challenged fundamental limits established by stellar theory. Scientists had to develop new models incorporating extreme convection processes and accelerated mass loss to explain how such a monster could even exist. The star's atmosphere contains natural masers, cosmic amplifiers that boost microwave signals like natural lasers. Water molecules and other compounds in VY Canis Majoris's turbulent atmosphere create intense beams of microwave radiation that allow astronomers to study the star's structure with extraordinary precision. These cosmic masers reveal wind velocities, rotation patterns, and three-dimensional structures impossible to detect through any other method. To truly grasp VY Canis Majoris's scale, imagine if it replaced our Sun, Earth, Mars, Venus, and Mercury would simply cease to exist as separate entities, dissolving into the star's atmosphere like sugar cubes dropped into an ocean. Even the gas giants Jupiter and Saturn would orbit within the star's outer layers, experiencing surface temperatures of thousands of degrees Celsius. The convection cells on this star's surface boggle the mind. Individual cells, like enormous bubbles of plasma rising and falling, have dimensions comparable to entire planetary orbits. These cosmic cauldrons transport material equivalent to dozens of suns from the star's interior to its surface, moving at velocities of tens of kilometers per second. A single convection cell contains more kinetic energy than the impact that created the Chicxulub crater and wiped out the dinosaurs. The energy output of VY Canis Majoris defies comprehension. It shines 270,000 times brighter than our Sun, producing energy equivalent to 1.8 trillion hydrogen bombs exploding every single second. Like a cosmic floodlight of unimaginable power, this star emits enough radiation to sterilize any rocky planet at distances where habitable zones would normally exist. Its total energy output exceeds that of entire dwarf galaxies. The stellar winds from VY Canis Majoris sculpt space itself across multiple light years. Material ejected at 50 kilometers per second creates complex structures that extend up to 7 light-years from the central star. Like a cosmic sculptor using stellar wind as a chisel, VY Canis Majoris has permanently modified the interstellar medium around it, creating arcs, shells, and filaments detectable across vast distances. In the nuclear furnace of VY Canis Majoris's core, temperatures and pressures allow fusion of elements as heavy as iron and cobalt. Like a cosmic alchemist's laboratory, this stellar core produces isotopes impossible to create on Earth. The nuclear processes follow reaction chains that terminate with the formation of the most stable, heavy atomic nuclei, creating a periodic table of elements that will eventually seed future solar systems. The star's fundamental instability makes it a ticking time bomb on a cosmic scale. VY Canis Majoris exhibits erratic and unpredictable brightness variations that indicate structural instability throughout its enormous bulk. Like a skyscraper built on unstable foundations, this stellar giant could undergo gravitational collapse without warning. When that happens, the resulting supernova will rank among the brightest ever observed from Earth. VY Canis Majoris was identified as a hypergigant only through the patient work of infrared astronomers who could peer through its dusty shroud. Like archaeologists uncovering a lost civilization buried under layers of sediment, this discovery revealed an entire population of stellar giants that had remained invisible to previous generations of astronomers. Infrared technology continues revealing hidden hypergigants scattered throughout our galaxy. Measuring VY Canis Majoris's true size required a combination of techniques including interferometry, photometry, and spectroscopic analysis. Like cartographers using multiple tools to map unknown territory, astronomers had to develop entirely new methods to study such an extreme object. These techniques now allow the study of other hypergigants with unprecedented precision. The entire evolutionary journey of VY Canis Majoris, from its birth on the main sequence to its current hypergigant phase, has lasted only 8 million years. Like an entire lifetime compressed into extreme fast-forward, this star has burned through fuel at rates that make human evolution appear glacially slow by comparison. Its next few thousand years will be even more dramatic as it approaches final collapse. VY Canis Majoris represents a crucial transition point in our cosmic journey, a bridge between the familiar supergiants like Betelgeuse and the truly extreme hypergigants we're about to encounter. Like an intermediate step on an impossible staircase, this star prepares our understanding for scales that will prove even more challenging to comprehend. The objects we'll discover next will make even VY Canis Majoris appear relatively modest, forcing us to abandon completely any remaining terrestrial perspectives about size and scale. We're about to meet a star that held the title of largest known for decades, forcing astronomers to completely rewrite their understanding of stellar limits. Discovered in 1860 in the constellation Scutum, UY Scuti was destined to become astronomy's heavyweight champion. With a radius 700 times that of our Sun, this hypergigant red giant was like the first skyscraper built in a city that had only known single-story buildings. When astronomers finally grasped UY Scuti's true dimensions, it redefined our entire concept of what large could mean in the stellar world. If we placed UY Scuti at the center of our solar system, it would engulf every planetary orbit out beyond Saturn. Our entire solar system would become a single, monstrous star. The Earth wouldn't just be vaporized, it would be deep inside this stellar atmosphere, along with Mars, Jupiter, and everything else we consider part of our cosmic neighborhood. The sheer volume of UY Scuti challenges human comprehension. This star contains approximately 5 billion times the volume of our Sun. Let me put that in perspective. UY Scuti could contain our Sun 5 billion times over, like a cosmic hangar of unimaginable proportions. This space could accommodate stellar populations equivalent to small dwarf galaxies. If each copy of our Sun were a grain of sand, UY Scuti would be like an entire beach compressed into a perfect sphere. But here's where UY Scuti becomes paradoxical in a way that perfectly demonstrates how extreme stellar physics defies our everyday intuition. Despite being 30 times more massive than our Sun, Scuti has an average density lower than Earth's atmosphere at an altitude of 50 kilometers. This star is essentially a gigantic cloud of hot gas held together by nothing but its own gravity. An astronaut flying through its outer layers would experience less resistance than walking through air at sea level. Scuti lurks 9,500 light-years away, so distant that despite its colossal size, it remains completely invisible to the naked eye. Like a lighthouse whose beam is dimmed by vast distance and interstellar dust, this stellar giant was only recognized as a hypergigant through detailed spectroscopic analysis. The light we observe from Scuti today began its journey toward Earth during humanity's Neolithic period, when our ancestors were just beginning to develop agriculture. This distant giant pulses with semi-regular variability over periods of 740 days, brightening and dimming in patterns that reveal fundamental instabilities in extreme stellar structures. Like a cosmic patient with irregular heartbeats, these pulsations indicate that Scuti is under tremendous internal stress. During its dimmest phases, the star can fade to magnitude 11, becoming invisible even to small telescopes. The energy production of Scuti operates on scales that dwarf everything we've encountered so far. This stellar furnace produces energy equivalent to 340,000 suns shining simultaneously, burning nuclear fuel at a rate that guarantees a short life even by stellar standards, like a massive engine operating far beyond safe specifications. Scuti converts matter into energy with an efficiency that challenges our traditional models of stellar physics. Its total energy output exceeds what entire civilizations could consume over trillions of years. When astronomers first determined Scuti's true size, the discovery instantly relegated all previous giant stars to the category of modest objects, like discovering that a familiar mountain is actually just a foothill compared to a distant mountain range. This revelation forced a complete recalibration of stellar scales. Scuti became the new measuring stick for truly colossal objects, the new standard against which astronomical gigantism would be judged. The atmospheric structure of Scuti defies easy description. Multiple layers with dramatically different temperatures, densities, and chemical compositions create a complex atmospheric system like a gas giant planet magnified trillions of times. The weather patterns in this atmosphere operate on incomprehensible scales. Individual storms could swallow entire solar systems whole. Scuti operates perilously close to fundamental physical limits, where radiation pressure from the star's core competes directly with gravitational forces trying to hold it together. Like a rope stretched to its breaking point, this battle between opposing forces maintains the star in a state of permanent instability. Any significant change in internal processes could trigger either catastrophic gravitational collapse or explosive disintegration. In Scuti's core, and temperatures exceed 100 million degrees, enabling fusion of heavy elements that rarely occur elsewhere in the universe. Like a cosmic laboratory for nuclear alchemy, this stellar furnace produces exotic isotopes of iron, cobalt, and nickel that will eventually spread throughout the galaxy. The nuclear processes occurring deep within create elements that will be incorporated into future generations of stars and planets. The scale of Scuti challenges our ability to create meaningful analogies. There simply aren't adequate comparisons in human experience to convey its size relative to our Sun. If our Sun were a human cell, Scuti would be larger than an entire city. If our Sun were a grain of sand, Scuti would be a mountain. Even these comparisons fail to capture the true magnitude of the difference, forcing us beyond familiar metaphors into purely mathematical descriptions. When Scuti finally explodes, and it will, relatively soon in cosmic terms, it will create a hyperluminous supernova that could outshine entire galaxies for weeks or months. Like fireworks on a cosmic scale beyond imagination, this explosion will be detectable from billions of light-years away. The elements forged in this stellar death will spread across hundreds of light-years, enriching the interstellar medium with materials for countless future star systems. Despite its enormous size, Scuti rotates incredibly slowly, taking several Earth years to complete a single rotation. This contrasts dramatically with our Sun's 27-day rotation period. Like a massive dancer moving in slow motion, this leisurely rotation results from conservation of angular momentum as the star expanded to its current size. Even at this slow rate, the star's surface still moves at hundreds of kilometers per second due to its colossal radius. The gravitational influence of Scuti extends across multiple light-years, affecting the motion of gas and dust throughout a vast region of space. Like an invisible hole in the fabric of space-time, this star bends the trajectories of passing objects even at distances where other stars would exert no detectable influence. Its gravity can capture and accelerate comets from entirely different star systems. Recent advances in astronomical measurement have forced scientists to revise their estimates of Scuti's size downward. Data from the Gaia satellite led to a recalculation that reduced its estimated radius to 755 times that of the Sun. Like a king dethroned by more precise measurements, Scuti temporarily lost its title as the largest known star. This revision demonstrates how advancing technology constantly refines our understanding of distant objects. Astronomers continue investigating whether Scuti might be part of a binary system, with a smaller companion star influencing its evolution. Like detectives searching for evidence of a cosmic crime, this investigation uses precise radial velocity measurements and photometric analysis. The discovery of a companion would explain some of the unusual characteristics in Scuti's evolution. Spectroscopic analysis of Scuti reveals elevated abundances of carbon, oxygen, and other heavy elements produced in its interior, like forensic analysis of a cosmic laboratory. This data reveals the star's evolutionary history and active nuclear processes. Spectral lines also show clear evidence of continuous mass loss through intense stellar winds. Computer simulations suggest that Scuti will collapse into a black hole within thousands of years, completely skipping the neutron star phase. Like cosmic weather forecasting, these models predict future evolution based on current conditions. The result will be a black hole with 15 to 25 times the mass of our Sun. High-resolution images reveal complex geometric patterns in the material Scuti has ejected over millennia. Like cosmic art created by physical processes, these structures include concentric arcs, dense knots, and radial filaments. The patterns suggest regular episodic ejections possibly related to pulsation cycles or magnetic activity. Although Scuti reigned as the largest known star for decades, recent discoveries have revealed objects even larger that once again challenge our concepts of stellar limits. Like a climber who reaches one peak only to discover an even higher mountain on the horizon, our journey through stellar scales is far from over. The true giants of the universe will make even Scuti appear modest by comparison, forcing us to stretch our understanding of scale to its absolute breaking point. In 2020, astronomers made a discovery that shattered every record we thought we understood about stellar gigantism. Located 19,000 light-years away in the constellation Scutum, Stephenson 2-18 was identified as the possible largest star known to science, with an estimated radius 150 times that of our Sun. like an archaeologist uncovering a pyramid that dwarfs the Great Pyramid of Giza. This revelation dethroned UY Scuti and once again redefined the limits of what we believed possible in our universe. If these measurements are confirmed, Stephenson 2-18 would make our sun appear like a single atom compared to a basketball. That's not hyperbole. The scale difference is literally that extreme. This stellar monster doesn't exist in isolation. Stephenson 2-18 resides within the Stephenson 2 star cluster, an extraordinary stellar nursery containing 26 red supergiants in unprecedented concentration. Like a royal family of cosmic giants all living in the same celestial neighborhood, this clustering suggests special conditions during star formation that we're still trying to understand. The entire cluster contains mass equivalent to 20,000 suns, packed into a region only 6 light-years across. The dimensions of Stephenson 2-18 challenge every attempt at comprehension. With a radius 150 times that of our Sun, this hypergigant has a diameter of approximately 3 billion kilometers. If we could somehow place it at the center of our solar system, its surface would extend beyond Saturn's orbit, completely engulfing Mercury, Venus, Earth, Mars, Jupiter, and Saturn, like a cosmic dome with planetary scale dimensions. This single star would transform our entire solar system into a single stellar entity. But here's where Stephenson 2-18 becomes paradoxical in ways that perfectly illustrate the alien physics of hypergigants. Despite its colossal size, this stellar giant contains only 12 to 25 times the mass of our Sun. It's like a gigantic balloon filled with incredibly thin air. The extreme expansion that characterizes the final evolutionary stages of hypergigants creates densities thousands of times lower than liquid water. The age of Stephenson 2-18 provides another stunning perspective. At approximately 17 million years old, this is actually a young star by cosmic standards, demonstrating just how rapidly massive stellar objects evolve. If Earth's entire 4.5 billion year history were compressed into a single year, Stephenson 2-18 would have been born just yesterday. Its relative youth contrasts dramatically with its extreme expansion, showing the accelerated pace of evolution in supermassive stars. The classification of Stephenson 2-18 continues to spark scientific debate. Its characteristics span the boundary between established categories, like discovering a new species that challenges existing taxonomy. This star forces astronomers to refine traditional definitions as its luminosity, temperature, and variability place it precisely on the border between recognized classifications. The energy output of Stephenson 2-18 reaches truly astronomical proportions. It shines 440 times brighter than our Sun, producing energy equivalent to entire small galaxies. Like a cosmic power plant operating far beyond its nominal capacity, this luminous output exceeds what advanced civilizations could consume over millions of years. The star's radiation heats interstellar material across distances measured in light-years. Stephenson 2-18 was discovered through systematic infrared surveys that could peer through cosmic dust obscuring visible light. Like X-rays revealing internal structures hidden from normal sight, infrared astronomy uncovered an entire population of hypergigants previously invisible to optical telescopes. Modern technology continues revealing hidden giants scattered throughout our galaxy. Observations show that Stephenson 2-18 experiences irregular variations in brightness, suggesting chaotic pulsations and episodic mass ejections. Like a cosmic patient with wildly erratic heartbeats. These fluctuations reveal fundamental instability in extreme stellar structures. Brightness changes can span multiple orders of magnitude over periods of decades, indicating processes beyond anything we observe in more stable stars. In the superheated core of Stephenson 2-18, advanced nucleosynthesis produces rare elements from iron to cobalt and nickel at industrial scales, like a cosmic refinery operating around the clock. This stellar furnace transforms hydrogen and helium into complex elements that will eventually form rocky planets. Each year, it produces iron equivalent to millions of metallic asteroids. Evolutionary models suggest that Stephenson 2-18 may collapse and explode as a hyperluminous supernova within just a few million years, like a cosmic bomb with its timer nearly expired. This star is rapidly approaching the moment when it can no longer support its own weight. The resulting explosion will rank among the brightest possible events in our local universe. The intense radiation and stellar winds from Stephenson 2-18 ionize and heat interstellar gas across a region spanning multiple light years. Like a gigantic cosmic heater, this star creates a bubble of hot gas that affects star formation throughout a vast region. Its influence can either suppress or accelerate the birth of future stellar generations, depending on local conditions. Measuring Stephenson 2-18's true size presents extraordinary challenges due to the dense envelope of dust created by the star itself. Like trying to measure a skyscraper through thick fog, astronomers must employ multiple techniques across different wavelengths. The uncertainties in these measurements mean the star's true size could be even larger than current estimates suggest. Convection cells on Stephenson 2-18's surface possess dimensions comparable to entire solar systems, transporting amounts of material equivalent to gas giant planets, like cosmic cauldrons boiling on an unimaginable scale. These convective motions generate complex magnetic fields and atmospheric structures. A single convection cell contains kinetic energy exceeding the impacts of massive asteroids. Stephenson 2-18 ejects material equivalent to Earth's entire mass annually through stellar winds traveling at tens of kilometers per second. Like a cosmic fountain constantly spraying material into space, this mass loss creates complex structures in the surrounding interstellar medium. Over its lifetime, the star may have ejected several solar masses of enriched material. The scale progression from our Sun to Betelgeuse to Stephenson 2-18 reveals an exponential expansion that challenges human visualization. Stephenson 2-18 is as much larger than Betelgeuse as Betelgeuse is larger than our Sun. Like cosmic Russian dolls where each level reveals incomprehensibly greater magnitude, this progression defeats our capacity for meaningful analogies. Even UY Scuti appears modest compared to these extreme dimensions. Computer simulations suggest that Stephenson 2-18 will consume its remaining nuclear fuel in less than 1 million years. Like a race car burning fuel at maximum throttle, this star operates at a pace that guarantees a spectacular end in the cosmic near future. The final stages of its evolution will occur on timescales that are geologically instantaneous. High-resolution images reveal that material ejected by Stephenson 2-18 forms complex, asymmetric patterns suggesting rotation or magnetic fields. Like cosmic sculpture created by invisible forces, these structures preserve a record of past stellar activity. The asymmetries may result from differential rotation or interactions with undetected stellar companions. Current measurements of Stephenson 2-18 involve significant margins of error, maintaining the possibility that the star could be even larger or smaller than present estimates. Like a scientific frontier where knowledge meets ignorance, this uncertainty illustrates the limits of our current technology. Future observations with advanced telescopes may dramatically confirm or revise our understanding. Stephenson 2-18 represents a crucial bridge between objects that are large but still measurable and phenomena that completely transcend human scales. Like the final stepping stone before a quantum leap in magnitude, This star prepares our understanding for scales where terrestrial analogies fail entirely. The objects we'll explore next will force us to abandon completely any remaining perspectives based on everyday experience, pushing us into realms where the very concepts of size and scale begin to break down. Here we encounter objects so extreme, so unstable, and so impossible that they challenge everything we thought we knew about stellar physics. Luminous blue variables like Eta Carinae and P Cygni represent a category of stellar extremism that shatters all conventional rules. During their most violent episodes, these cosmic shapeshifters can temporarily expand to radii of 3,000 to 5 times that of our Sun, dimensions that would make even Stephenson 2 to 18 appear modest. Like cosmic transformers that radically alter their form, these LBVs defy traditional classifications and can temporarily exceed any stable star in sheer size. The most famous example remains Eta Carinae's spectacular eruption in 1843. This event was so violent that the star temporarily became the second brightest in Earth's sky, creating the distinctive homunculus nebula that we can still observe today. During this cosmic tantrum, Eta Carinae ejected material equivalent to 10 to 40 solar masses in just a few decades, expanding to dimensions that would dwarf every hypergigant we've discussed. Like a cosmic volcano in maximum eruption, this event demonstrated that stars can grow far beyond normal limits during periods of extreme instability. Even more dramatic are the luminous red novae, events like V838 Monocerotis in 2002, which showed us stars expanding rapidly to radii of 1,570 times the Sun's in mere months. Like cosmic balloons inflating at impossible speeds, these expansions can temporarily create objects larger than any stable hypergigant. V838 Monocerotis transformed from a relatively ordinary star into an extreme supergiant in just a few years, proving that stellar size can change drastically on human timescales. P Cygni, located 6,000 light-years away, demonstrates the ultimate in stellar instability, with 60 times the Sun's mass and luminosity 610,000 times greater. This luminous blue variable can expand to radii of 4,000 times the Sun's during periods of maximum activity. Like a cosmic giant that dramatically grows and shrinks, P Cygni proves that the largest stars aren't necessarily stable objects, but rather chaotic, shape-shifting monsters. Theoretical models push us even further into the realm of the impossible. The very first stars in the universe, population 3 stars formed from pure hydrogen and helium, could have reached masses of 300 to 1,000 times that of our Sun. These primordial titans, existing more than 13 billion years ago, would have expanded to radii of 10,000 to 100,000 times the Sun's during their final phases. Like giants from a cosmic mythology, these impossible stars shape the evolution of the entire universe and can never form again now that space is enriched with heavier elements. WR 102K represents stellar physics pushed to its absolute breaking point. This Wolf-Rayet star burns with surface temperatures of 210,000 Kelvin while ejecting material at velocities of 5,000 kilometers per second, creating stellar winds with unimaginable kinetic energy. During periods of instability, it can temporarily expand to hypergigant dimensions while maintaining these extreme temperatures, like a cosmic blowtorch operating at maximum power. WR102K produces energy equivalent to 3.2 million suns in a structure that constantly changes shape. Symbiotic star systems like our Aquarii create structures that transcend individual stellar boundaries. These cosmic partnerships consist of a red giant transferring material to a compact companion, forming complex structures that can exceed the dimensions of any single star. During accretion outbursts, material forms disks and jets extending tens of astronomical units. like an intricate cosmic dance between mismatched partners. These systems create structures larger than any isolated star could achieve. Computer simulations of the early universe reveal even more extreme possibilities. In the primordial cosmos, extremely rapid accretion could have formed protostars with masses exceeding 10,000 times the Sun's before nuclear fusion even began. These protostellar embryos would have had radii comparable to outer planetary orbits, existing as brief but enormous concentrations of matter, like cosmic giants that never quite learned to walk. These transient structures represent the largest possible stellar concentrations. Near the center of our galaxy lurks Pistol Star, a hypergigant with 150 times the Sun's mass and luminosity 1.7 million times greater. During periods of maximum activity, this stellar monster ejects material so rapidly it creates the Pistol Nebula, visible across light years of space. Like a cosmic geyser in permanent eruption, Pistol Star can temporarily expand its outer layers to dimensions exceeding conventional hypergigants. When massive stars collide and merge, they create temporary objects with characteristics impossible for any individual star. During the merger process, the resulting structure can expand to extreme dimensions before settling into a new, stable configuration, like cosmic accidents creating temporary monstrosities. These stellar collisions produce the largest possible stellar objects for brief but spectacular periods. IRC PUS-1420 represents stellar classification pushed beyond its limits. This unique object exhibits characteristics placing it somewhere between supergiants and luminous blue variables, with radii varying between 1,200 and 4,500 times the Sun's. During periods of maximum instability, IRC PUS-1420 can temporarily become one of the largest stellar structures known, like a cosmic chameleon constantly changing appearance. This star demonstrates that stellar classifications have fundamental limitations. Supernova imposters, like Eta Carinae's great eruption, create massive ejected envelopes that can temporarily form structures with radii thousands of times the Sun's. During these events, stars don't explode completely, but eject material so massively they create temporary giants, like cosmic fireworks that refuse to fully explode. These events temporarily create the largest objects associated with individual stars. Theoretical physics pushes us into even stranger territory. Hypothetical quark stars composed of exotic matter might exhibit properties including expansion to impossible sizes. These speculative structures could temporarily achieve dimensions, making hypergigants appear minuscule before collapsing or exploding. Like science fiction based on real physics, quark stars represent the absolute theoretical limits of what might be possible. During periods of extreme activity, even familiar giants like VY Canis Majoris might expand beyond their already extreme normal dimensions, potentially reaching radii exceeding 2,000 times the Sun's. Like giants experiencing sudden growth spurts, these temporary expansions could make them larger than any other known star. Historical observations suggest size variations much greater than current conservative estimates. Magnetars and other stars with extreme magnetic fields might temporarily sustain stellar structures impossible under normal conditions. Magnetic fields trillions of times stronger than Earth's could support unstable stellar architectures for brief periods. Like cosmic magnets creating impossible structures, these stars might temporarily assume configurations that defy conventional models. Our Coronae Borealis variables can change in size and luminosity across 9 magnitudes, dramatically altering their physical structure over short periods. During maximum expansion, they can reach hypergigant dimensions before contracting again, like stars experiencing identity crises. These extreme variables demonstrate remarkable plasticity in stellar structures. When giant stars encounter black holes, they can form temporary hybrid structures with extreme properties. Material being accreted can create disks with dimensions exceeding any individual star. Like deadly dances between giants and invisible monsters, these encounters temporarily create structures larger than any isolated star. Pair instability supernovae in stars with masses between 140 and 260 solar masses create cyclic explosions where stars repeatedly eject outer layers and expand to extreme dimensions before contracting. Like cosmic giants experiencing convulsions, these cycles can temporarily create structures exceeding any stable hypergigant. Theoretical models of primordial helium stars suggest they could have achieved radii tens of thousands of times the Sun's during certain evolutionary phases. Like extinct species of cosmic giants, these impossible stars represent absolute limits of what physics permits. We've now explored objects that have transcended the traditional boundaries of what we consider stars, forcing us to question our very definitions. Like explorers who've discovered territory beyond known maps. We've reached a frontier where individual stellar objects begin to rival galactic structures in scale. The scales we'll encounter next will completely transcend concepts based on isolated stars, entering a realm of cosmic phenomena that operate by fundamentally different rules. If all the stars we've explored were grains of sand, the structures we're about to encounter would be entire mountains built from those grains. Here we encounter the absolute physical limits that govern what can exist in our universe. Fundamental physics imposes maximum boundaries where objects cease to be stars and transform into something completely different, like an invisible barrier separating the possible from the impossible. This limit is determined by the speed of light, gravitational constants, and maximum radiation pressure. Beyond this point, matter behaves according to rules so alien they defy any intuition based on everyday experience. We've entered the realm of quasi-stellar structures that challenge our very definitions. Objects balanced on the threshold between stars and other cosmic phenomena possess properties that refuse to fit traditional categories. Like mythical creatures combining characteristics of different species, these structures force us to create entirely new classifications. Gigantic accretion disks, massive ejected envelopes, and extreme star-forming regions create objects larger than any individual star could ever become. Modern supercomputers allow us to model conditions so extreme they're impossible to replicate or observe directly, revealing the fundamental limitations built into nature itself, like microscopes that peer into the very structure of reality. These simulations show us that the universe contains absolute constraints. Beyond certain combinations of size, mass, and energy, objects simply cannot exist without violating the fundamental laws of physics. When mass concentration exceeds critical thresholds, the very fabric of space-time begins to curve beyond recovery. Like an elastic surface stretched past its breaking point, this extreme curvature creates singularities where our known physics simply stops functioning. At these points, our familiar concepts of size, time, and cause and effect lose all traditional meaning. In dimensions this extreme, relativistic effects become completely dominant, causing time itself to flow differently in different regions of the same object, like a cosmic clock that somehow ticks at different rates simultaneously. These temporal distortions mean that separate parts of extreme structures exist in entirely different temporal rhythms. Observers positioned at different locations would experience the passage of time in completely different ways. On the surfaces of objects this massive, the velocity needed to escape gravitational pull approaches the speed of light itself, creating conditions where Newtonian physics fails catastrophically, like a gravitational prison approaching perfection. This means that light itself requires significant time to escape from the surface. Photons emitted by the stellar surface might take years to emerge from the outer atmospheric layers. Objects with such extreme masses and accelerations generate detectable gravitational waves that travel at light speed through the fabric of space-time itself, like cosmic bells ringing through the very structure of reality. These waves carry information about the universe's most violent events. The detection of gravitational waves has opened an entirely new window for studying objects impossible to observe through any other method. Even objects of seemingly impossible mass eventually evaporate through Hawking radiation, demonstrating that even apparently permanent structures have finite lifespans, like massive glaciers melting in extreme slow motion. This evaporation occurs over timescales that make the lifetimes of stars appear instantaneous. This process fundamentally connects quantum mechanics with general relativity in ways we're still struggling to understand. In structures this large, quantum fluctuations in the vacuum can produce measurable macroscopic effects, connecting the subatomic world with galactic-scale structures. Like cosmic butterflies creating hurricanes through quantum butterfly effects. These fluctuations demonstrate fundamental connections between the smallest and largest scales in nature. Quantum uncertainty manifests itself across astronomical distances. On truly cosmic scales, dark energy becomes the dominant force, accelerating the expansion of space itself at an ever-increasing rate. Like an invisible engine driving the entire cosmos, this mysterious force will eventually separate all structures not bound by gravity. Its dominance marks the transition from object physics to the physics of the universe as a unified whole. Extreme distances bring us close to the cosmological horizon, the boundary beyond which information cannot reach us due to the expansion of space. Like a horizon on an infinite ocean that constantly recedes, this fundamental limit means portions of the universe remain forever inaccessible. Structures beyond this horizon exist, but can never be observed or influence our cosmic region. In sufficiently large dimensions, the time required for information to travel from one end to another exceeds the timescales relevant for physical processes. Like a nation so vast that its capital cannot effectively govern distant provinces, such objects cannot function as coherent entities. Different regions evolve independently without any possibility of coordination. There exists a critical scale where the physics of individual objects gives way to cosmology, marking a fundamental boundary between different regimes of knowledge. Like crossing a border between countries with completely different laws, this transition requires abandoning familiar concepts entirely. Beyond this scale, individual objects become irrelevant compared to the properties of the universe as a whole. Physical laws contain automatic mechanisms that prevent unlimited growth of structures, creating natural limits for the maximum size of objects. Like a cosmic thermostat regulating universal temperature, these instabilities ensure the universe maintains its observed characteristics. Radiation pressure, gravitational instabilities, and quantum effects work together to impose absolute boundaries. In sufficiently massive objects, gravitational binding energy becomes comparable to the rest mass energy of matter itself, making the distinction between mass and energy meaningless. Like cosmic accounting, where debits and credits become indistinguishable. This fundamental equivalence changes the very nature of matter. Objects become more gravitational energy than conventional material. Supermassive black holes containing billions of solar masses represent the maximum possible concentrations of matter in our current universe. Like cosmic drains that can swallow entire galaxies, these objects mark the final transition between stars and singularities. Their event horizons can exceed the orbits of entire stellar systems, yet they represent the complete collapse of conventional structure. at the centers of extremely compact objects. Infinite density destroys information irreversibly, violating fundamental principles of quantum mechanics. Like informational black holes that erase history itself, these singularities represent absolute limits of knowledge. Known physics literally ceases to function at these points, requiring completely new theories. Modern theories suggest the possibility of extraspatial dimensions that could harbor structures impossible in our familiar 3 dimensions. Like secret rooms hidden within a familiar house, these extra dimensions could contain objects that completely transcend observable scales. String theory and M theory predict possibilities that would make our largest known structures appear subatomic. We have reached the point where physics itself, not technology, imposes fundamental limits on what can exist in the observable universe. Like explorers who've arrived at the edge of a continent only to discover an infinite ocean beyond. We recognize that certain frontiers are absolute. Beyond this point, we don't encounter larger objects, but rather the complete breakdown of concepts like size, time, and individual existence into something entirely different, the cosmos itself. Now that we've touched the absolute limits of what physics allows to exist, we must confront the profound implications of our cosmic journey. Standing before the scales of Stephenson, 218, and the impossible structures beyond, we're forced to recognize that our everyday perspective is fundamentally limited, like ants suddenly discovering they live on a planet rather than on an island. This revelation about cosmic scales demands a complete re-evaluation of our relative importance. Earth itself could fit trillions of times within the largest stellar structures we've explored, making our entire planet less significant than a grain of cosmic dust. Yet this cosmic humility transforms rather than diminishes us. Here lies the central paradox of our existence. Although we are microscopically small compared to cosmic structures, we remain unique as the only known form of matter capable of contemplating these scales. Like impossible observers in an impossible universe, we represent something extraordinary. Atoms organized in such a way that they can comprehend galaxies. Our physical insignificance contrasts dramatically with our intellectual capacity to map the entire cosmos. Consider the statistical miracle of conscious life. Given the extreme conditions required to form habitable planets near stable stars, consciousness may be incredibly rare in the universe. We exist as winners of an impossible cosmic lottery, the result of a sequence of coincidences so improbable it defies comprehension. Most of the stellar giants we've explored are engines of destruction that would make life impossible anywhere in their vicinity. The perspective of cosmic time further humbles us. All of human civilization represents less than an eye blink in the lifetime of stars like Betelgeuse. If Betelgeuse's existence were a single year, all of recorded human history would occupy less than 1 second. This temporal perspective reveals that events we consider monumentally important are cosmic instantaneous, forcing us to recalibrate our scales of importance and urgency, yet we are intimately connected to these stellar giants. Every atom in your body except hydrogen was forged in the nuclear cores of massive stars or supernova explosions. We are literally children of the stars, stellar dust organized in a way that allows us to contemplate our origins. The carbon in your DNA, the iron in your blood, the oxygen you breathe, all were born in the nuclear furnaces of hypergigants billions of years ago. Our biosphere appears extraordinarily fragile against cosmic forces. Earth's atmosphere and oceans form a film thinner than an eggshell compared to our planet, which is itself invisible compared to stellar structures, like a soap bubble floating in a hurricane. The terrestrial biosphere is exquisitely vulnerable to cosmic forces. A nearby supernova or close passage by a hypergigant would be sufficient to extinguish all terrestrial life instantly, as possibly the only form of matter capable of understanding the universe. We carry extraordinary responsibility to preserve and expand knowledge. We are the universe becoming conscious of itself, representing billions of years of cosmic evolution, culminating in the capacity for self-reflection. The extinction of human consciousness would mean the universe would return to existing without any observer capable of contemplating its magnificence. The physics governing atoms in our bodies is intimately connected with the processes that create and destroy hypergigants. Like a cosmic symphony where each individual note contributes to total harmony. We understand that the smallest and largest scales of nature are fundamentally intertwined. Quantum fluctuations during the Big Bang created the seeds that eventually formed the largest cosmic structures. Confronted with scales that make our existence statistically impossible, we naturally question whether the universe has purpose or whether we represent an extraordinary cosmic accident. Like philosophers contemplating infinity itself, we face questions that transcend science. Why does anything exist rather than nothing at all? Our capacity to ask these questions may be more significant than any possible answers. Technology serves as our bridge to the cosmos. Telescopes and computers allow beings standing 7 meters tall to study objects billions of times larger and more distant. Like cosmic extensions of our limited senses, these tools demonstrate humanity's unique capacity to transcend biological limitations. Through technology, we can touch impossible scales and bring the universe within our comprehension. The vastness of stellar space intensifies our search for extraterrestrial life with existential urgency, like castaways on an infinite ocean searching for other survivors. We investigate whether other forms of consciousness contemplate the same stellar giants. The discovery of intelligent life would be less scientifically than existentially significant, proving we are not completely alone. The knowledge and art we create may be unique in the universe, making cultural preservation a matter of cosmic significance. Like guardians of a universal library, we bear responsibility for keeping the flame of understanding alive against indifferent vastness. Our music, literature, and science may represent the only conscious manifestations of beauty in a cosmos dominated by blind, physical processes. Although individuals live for less than a cosmic breath, our species could potentially survive for billions of years if we avoid extinction. Like individual cells contributing to an immortal organism, each human life contributes to the larger project of cosmic understanding. Our descendants may eventually travel to other stars, carrying consciousness beyond our solar system. In billions of years, humanity's descendants may evolve into completely different forms, possibly capable of comprehending even larger scales. Like distant ancestors who couldn't imagine modern technology, we represent only an initial stage in an evolutionary journey that might carry consciousness to cosmic levels. Future forms of intelligent life may develop capabilities we would consider magical today. The distances to hypergigants, like Stephenson 2.18, require technologies that challenge known physics, making direct exploration possibly impossible. Like dreaming of flight before discovering aerodynamics, our fantasies of interstellar travel face fundamental barriers. Even at light speed, journeys to these stars would require tens of thousands of years, exceeding all of recorded civilization. Radio signals to distant stars would take decades or centuries to arrive, making real-time communication impossible. Like sending letters to correspondents who might die before replies arrive. Interstellar communication requires temporal perspectives transcending individual lives. Conversations between stellar civilizations would occur on geological rather than human timescales. The scientific knowledge we develop about stellar scales may survive far beyond our civilization, preserved for future intelligent species, like builders of monuments lasting millennia. Scientists create understanding that may be our most enduring contribution to the cosmos. The physical laws we discover are eternal truths that could be rediscovered by any sufficiently advanced civilization. Contemplating stellar scales inspires art, music, and literature that capture our emotional response to infinity. Like artists attempting to paint the impossible, we create works that translate cosmic grandeur into comprehensible human experiences. This cosmic art may represent a unique way of psychologically processing our position in the universe, transforming cosmic terror into wonder and beauty. Understanding stellar scales forces development of philosophies incorporating cosmic vastness into human value systems. Like ancient sages contemplating infinity with modern tools, we develop ethics and meanings that acknowledge our physical smallness while celebrating our uniqueness as conscious observers. These philosophies may be necessary for maintaining mental health in the face of immensity. Ultimately, we come to recognize that being small before the cosmos doesn't diminish the value of human experience. It makes it more precious through its rarity. Like a unique flower blooming in an infinite desert, our existence gains meaning precisely through its improbability and fragility. Understanding stellar scales doesn't make us insignificant, but rather conscious participants in the greatest possible spectacle, the evolution of the universe itself. Now we must make the profound journey back through the scales we've explored, returning mentally from Stevenson 2:18 to Betelgeuse, then to our Sun, and finally to Earth. Like an astronaut returning to our planet after contemplating the vastness of space, we experience a deep psychological transformation. Our perception of scale has been permanently altered. What once seemed immense now appears intimate, creating a renewed appreciation for small, nearby details. The everyday concerns that once consumed our thoughts, work pressures, relationship difficulties, personal challenges, gain entirely new perspective when measured against the scales we've explored. Like mountains that reveal themselves as mere hills when viewed from an airplane, human problems don't disappear, but assume more manageable proportions. This cosmic perspective offers a powerful tool for distinguishing between truly important issues and temporary anxieties. After contemplating the relative simplicity of stellar giants burning hydrogen in massive nuclear furnaces, we develop renewed appreciation for the extraordinary complexity of terrestrial life. Like admiring the delicate mechanics of a watch after observing the operation of a massive engine, we realize that complexity doesn't always correlate with size. Earth concentrates more diversity and organization than entire galaxies filled with simple stars. Although we are cosmically minuscule, human scale remains the necessary reference point for giving meaning to any measurement or experience. Like a universal unit of measurement for consciousness, human perspective proves indispensable even when studying structures trillions of times larger. Without human scale as our starting point, cosmic scales would lose all comprehensible meaning. The telescopes and instruments that allowed us to explore hypergigants represent dramatic extensions of our naturally limited sensory capabilities. Like tools that transform humans into cosmic beings, these technologies demonstrate our unique capacity to transcend biological limitations. Through technology, human consciousness weighing 4 kilograms can map structures weighing trillions of times more than entire planets. Information about stellar giants is now available to anyone with internet access, democratizing knowledge that was once the exclusive privilege of specialists. like a cosmic library open to everyone. This democratization means any individual can develop profound cosmic perspective. A child with a smartphone has access to more knowledge about the universe than any scientist possessed a century ago. Those of us who have grasped stellar scales carry the responsibility of sharing this transformative perspective with others. Like travelers returning with maps of unknown territories, we bear an obligation to expand our species' horizons. Cosmic perspective can serve as an antidote to the artificial divisions that separate humanity, revealing our fundamental unity in the face of vastness. Education about cosmic scales should become a fundamental component of learning, providing mental tools for dealing with the complexity of the modern world, like a gymnasium for developing mental muscles. Scientific education about scales trains our capacity to think beyond everyday limitations. Students who understand stellar scales develop mental flexibility applicable to any complex problem. Knowledge about hypergigants inspires a new generation of artists attempting to capture and communicate experiences of impossible scales. Like painters trying to represent dimensions beyond normal perception, artists develop visual and poetic languages to translate the cosmos into human experience. This cosmic art can bridge the gap between scientific knowledge and emotional understanding. Understanding stellar scales forces the development of personal philosophies that incorporate cosmic vastness into daily decisions. Like ancient sages using astronomical knowledge to guide practical life, we develop ethics that acknowledge our smallness while recognizing our unique responsibilities. Important decisions gain new dimensions when considered in the context of billions of years and trillions of stars. Studying hypergigants creates deep emotional bonds with the universe that transcend mere factual information. Like developing friendship through mutual understanding, scientific knowledge generates genuine affection for the cosmos. Betelgeuse becomes familiar rather than merely distant. Vivae Canis Majoris inspires admiration rather than just amazement. The universe becomes home rather than hostile environment. Exploring stellar scales reveals the vastness of our ignorance, cultivating intellectual humility essential for scientific progress. Like climbers who reach one peak only to discover an infinite mountain range, we recognize that every answer reveals 10 new questions. This humility protects against intellectual arrogance and keeps minds open to future discoveries. Understanding that we may be unique in our capacity to study the cosmos creates powerful motivation to preserve and expand scientific civilization. Like guardians of a unique flame in the universe, we bear extraordinary responsibility for maintaining human knowledge. Wars, climate change, and other threats gain additional urgency when we consider they might extinguish the only known form of cosmic consciousness. Comprehending that cosmic structures evolve over millions and billions of years cultivates patience for long-term projects. Like gardeners planting trees for future generations, we develop temporal perspective that values gradual progress over immediate gratification. Important social and scientific changes require persistence measured in decades, not months. After exploring the violence and instability of hypergigants, we develop new appreciation for the relative stability of our sun and solar system. Like storm survivors, appreciating calm weather, we recognize that stable conditions necessary for life are extraordinarily rare in the cosmos. Our location in the habitable zone of a stable star represents cosmic good fortune that should inspire gratitude rather than complacency. Professional and personal problems maintain practical importance, but lose their capacity to cause profound existential despair. Like actors who recognize their performing roles in a larger play, we maintain commitment to our performances while recognizing the greater context. Individual failures become temporary episodes in the much larger story of consciousness exploring the cosmos. Recognition that we all share the same stellar origins and cosmic destiny strengthens bonds between individuals and cultures. Like castaways in the same boat on an infinite ocean, cultural and political differences seem less important than the collective survival of consciousness. Nationalities, religions, and ideologies become local variations within a single species, contemplating the cosmos. Human minds exposed to cosmic scales develop flexibility and creativity applicable to any complex problem. Like muscles strengthened through progressive exercise, mental capacity grows when challenged by concepts that stretch understanding. People who comprehend hypergigants develop abilities to think beyond conventional limitations in any area of human life. Understanding stellar scales marks not an end, but the beginning of a personal scientific journey that can last an entire lifetime. Like opening a portal to infinite territory of discovery, this cosmic perspective creates an insatiable appetite for knowledge. Each new discovery about the cosmos becomes more meaningful when contextualized within our expanded understanding of reality's fundamental scales. Our cosmic journey has prepared us for this final transformation. We return now to Betelgeuse, the star that began our extraordinary exploration, but we see it with eyes completely transformed by experience. Like a traveler returning to their hometown after years exploring the world, we recognize familiar places but with an entirely new perspective. Betelgeuse is no longer simply a big star, but rather a specific step in a cosmic ladder of unimaginable magnitudes that we now understand intimately. Our journey has revealed an extraordinary progression, from our Sun to Betelgeuse, 700 times larger, to VY Canis Majoris, 420 times larger, to Stephenson 2 to 18, 150 times larger, with each leap representing an exponential multiplication of our understanding, like a mathematician discovering an infinite sequence. We realize that cosmic scales follow patterns that challenge intuition while obeying fundamental physical laws. Each star represents not merely an individual object, but a window into understanding the limits and possibilities of our universe. We've learned a profound lesson about scientific humility. Every largest known star we explored was eventually superseded by an even larger discovery, teaching us that scientific knowledge is a continuous process of revision and expansion. Like scientists learning that today's certainties may become tomorrow's limitations, we develop the intellectual humility that is essential for progress. Stephenson 2 to 18 may not remain champion forever, reminding us that the universe always holds surprises for observers who are sufficiently patient and technologically advanced. We now understand the intimate connection between the smallest and largest scales. The atoms in our bodies were forged in the nuclear cores of the same hypergigants we've studied, creating a direct physical connection between human and cosmic scales. Like recognizing distant relatives at a universal family reunion, we realize we are literally made from materials processed by Betelgeuse, VY Canis Majoris, and their giant siblings, the iron in our blood, calcium in our bones, and oxygen in our lungs were born in stellar furnaces billions of years ago. All of human civilization represents a minuscule fraction of the lifetimes of the stars we've studied, providing profound temporal context for evaluating the relative importance of contemporary events. Like observing human history through a temporal telescope, we recognize that crises dominating today's headlines are brief episodes in a much larger narrative. This perspective doesn't diminish the importance of human issues, but offers balancing context for our anxieties and urgencies. As possibly the only form of matter in the local universe capable of contemplating stellar scales, We carry extraordinary responsibility to preserve and expand this capacity. We are the universe becoming conscious of itself, representing billions of years of cosmic evolution, culminating in the capacity for self-reflection. The extinction of human consciousness would mean that trillions of stars would return to existing without any observer capable of contemplating their magnificence. When we consider the vastness we've explored, we must remember that consciousness, this ability to understand and appreciate cosmic scales, is the universe's most remarkable achievement. We are 1.4 kilograms of organized matter that can comprehend objects trillions of times more massive. This achievement transcends any individual human accomplishment, representing something so extraordinary it borders on the miraculous. Detailed knowledge about the structure, evolution, and destiny of hypergigants doesn't diminish, but rather tremendously amplifies our appreciation of their beauty. Like a musicologist who understands the complex composition of a symphony, scientific knowledge reveals layers of elegance invisible to casual observers. Betelgeuse, glowing in Orion's shoulder, now carries an epic story of birth, evolution, and impending death that enriches every telescopic observation. All human beings, regardless of culture, nationality, or beliefs, share the same stellar origins and contemplate the same cosmos filled with hypergigants. Like inhabitants of the same planet orbiting the same star in a galaxy filled with similar objects, our superficial differences pale before our shared cosmic heritage. Stellar perspective reveals that we are all descendants of the same nuclear furnaces, contemplating the same cosmic spectacle. The telescopes and instruments that allowed us to explore distant hypergigants represent dramatic extensions, not just of our senses, but of human consciousness itself. Like tools that transform limitations into infinite possibilities. Scientific technology demonstrates humanity's unique capacity to transcend biological conditions. Through science, 1.4 kilograms of consciousness can map structures trillions of times more massive than entire planets. This technological amplification of human awareness represents one of evolution's most extraordinary achievements. We have transformed from primates aware only of immediate surroundings into beings capable of contemplating the largest structures in the universe. Through instruments, we've extended our perception across impossible distances, allowing consciousness to touch scales that should be forever beyond biological reach. Knowledge about stellar scales should be the heritage of all humanity, not the privilege of specialists, because it offers transformative perspective applicable to every aspect of life, like a mental tool that expands cognitive capabilities. Education about cosmic scales trains the human mind to deal with the complexities of the modern world. A child who understands the dimensions of Stevenson 2 to 18 develops mental flexibility applicable to any future problem. This democratization of cosmic knowledge represents a revolution in human potential. For the first time in history, anyone with access to basic technology can develop profound cosmic perspective. This widespread cosmic literacy may be essential for humanity's future survival and growth as a species capable of understanding its place in an infinite universe. Our journey through stellar scales creates an insatiable appetite for future discoveries, motivating new generations of astronomers and scientists, like opening a portal to infinite territory of mysteries. This cosmic perspective guarantees that the search for knowledge will continue as long as human consciousness exists. Future telescopes will reveal even larger hypergigants, planets orbiting giant stars, and phenomena we can barely imagine today. The next generation of space telescopes will peer deeper into cosmic history, potentially revealing population 3 stars, those primordial giants that may have exceeded even Stevenson 218 in size. We may discover stellar structures so extreme they challenge our current understanding of what's physically possible. Each new revelation will expand our comprehension of cosmic scales even further. Contemplating hypergigants inspires art, music, and literature that attempt to capture our emotional response to infinity in forms comprehensible to human experience. Like artists trying to translate cosmic symphony into terrestrial language, creators develop new ways to express wonder, terror, and beauty in the face of vastness. This cosmic art may be the unique cultural contribution of the first species to understand stellar scales. Consider how cosmic perspective has already begun transforming human culture. Poetry speaks of stellar distances. Music incorporates cosmic themes, and visual art attempts to capture the sublime beauty of nebulae and hypergigants. This represents the emergence of truly cosmic culture. Art informed by scientific understanding of scales that dwarf all previous human experience. Understanding stellar scales forces the development of philosophies that incorporate cosmic vastness into practical human value systems. Like sages who contemplate infinity but must live in the finite, we develop ethics that recognize our physical smallness while acknowledging our unique responsibility as conscious observers. Important decisions gain new dimensions when considered in the context of billions of years and trillions of stars. These cosmic philosophies may prove essential for humanity's psychological health as we continue expanding our understanding of universal scales. They provide frameworks for maintaining meaning and purpose despite our apparent cosmic insignificance, showing us that consciousness itself represents the universe's greatest achievement. After exploring the violence and instability of hypergigants, we develop profound appreciation for the exceptional stability of our sun that made life possible. Like castaways who found a safe island in a stormy ocean, we recognize that conditions necessary for consciousness evolution are extraordinarily rare in the cosmos. Our location in the habitable zone of a stable star represents a cosmic lottery that should inspire gratitude and responsibility. The knowledge about stellar scales that we've developed will be transmitted to future generations, who will expand it far beyond our current understanding. Like cosmic librarians preserving wisdom for descendants, we participate in an intellectual project that may last millions of years. Our great-grandchildren may travel to other stars, carrying the cosmic perspective we've developed into territories unimaginable today. Understanding that all the hypergigants we've studied will eventually explode or collapse offers balancing perspective on universal impermanence. Like cosmic Buddhists contemplating transience on a galactic scale, we learn to appreciate current beauty while accepting inevitable change. Even Stevenson 2:18 is temporary, reminding us that excessive attachment to any particular configuration is illusion. This acceptance of cosmic impermanence paradoxically makes our temporary existence more precious, not less. Knowing that even hypergigants are ephemeral helps us appreciate the extraordinary rarity and beauty of conscious experience in a universe dominated by unconscious physical processes. If human consciousness managed to comprehend scales of trillions of kilometers starting from a 1.7-meter perspective, what other apparent limitations can we transcend? Like proof of concept that human minds can dramatically exceed initial conditions, stellar scales motivate attacks on other seemingly impossible problems. Consciousness that maps hypergigants may eventually solve any mystery sufficiently approached. Our journey through known scales prepares human minds for future discoveries that may be even more transformative than hypergigants. Like athletes training for future competitions, we expand mental capacity to deal with revelations we can't currently imagine. The universe has always held surprises for observers, and our generation is preparing mental ground for the next revolutions in understanding. The curiosity that led us from Betelgeuse to Stephenson 2 to 18 represents a fundamental force driving consciousness evolution in the universe. Like energy that transforms inert matter into active observers, curiosity may be the cosmos's most important property. Without curiosity, trillions of stars would exist without any being capable of contemplating their magnificence or questioning their mysteries. This curiosity represents evolution's greatest triumph, the development of matter capable of understanding matter, of universe becoming conscious of universe. Through human consciousness, the cosmos has developed eyes to see itself, minds to comprehend itself, and hearts to appreciate its own beauty. We reach our final synthesis. Although we are microscopically small compared to the scales we've explored, our capacity to understand them demonstrates that greatness isn't measured solely in kilometers or kilograms. Like living proof that consciousness transcends physical limitations, we represent something extraordinary, atoms organized in such a way that they can map galaxies. Our physical smallness becomes irrelevant compared to our infinite capacity to understand, question, and admire the cosmos that surrounds and created us. Now we begin the most meaningful part of our cosmic journey, the return home with transformed understanding. We come back to Betelgeuse, the star that initiated our extraordinary exploration, but we see it with eyes completely transformed by experience. Like a traveler returning to their hometown after years exploring distant continents, we recognize familiar celestial landmarks, but with an entirely new perspective. Betelgeuse is no longer simply a big star twinkling in Orion's shoulder. It has become a specific step in a cosmic ladder of unimaginable magnitudes that we now understand intimately. Our journey has revealed an extraordinary progression that follows mathematical beauty. From our Sun to Betelgeuse, 700 times larger, to VY Canis Majoris, 420 times larger, to Stephenson 2 to 18, 150 times larger, with each leap representing an exponential multiplication of our understanding. Like a mathematician discovering an infinite sequence hidden in nature's architecture, we realize that cosmic scales follow patterns that challenge intuition while obeying fundamental physical laws. Each star represents not merely an individual object burning in space, but a window into understanding the absolute limits and possibilities of our universe. We've absorbed a profound lesson about scientific humility that will serve us throughout our lives. Every largest known star we explored was eventually superseded by an even more colossal discovery, teaching us that scientific knowledge is a continuous process of revision and expansion rather than a collection of fixed truths. Like scientists learning that today's certainties may become tomorrow's quaint limitations, we develop the intellectual humility that proves essential for genuine progress. Stephenson 2:18 may not remain champion forever, reminding us that the universe always holds surprises for observers who remain sufficiently patient and technologically ambitious. We now understand the intimate, almost mystical connection between the smallest and largest scales in nature. The atoms composing our bodies were forged in the nuclear cores of the same types of hypergigants we've studied, creating a direct physical connection between human and cosmic scales that transcends mere academic knowledge. Like recognizing distant relatives at a universal family reunion, we realize we are literally constructed from materials processed by ancient versions of Betelgeuse, VY Canis Majoris, and their giant siblings. The iron flowing through our bloodstream, the calcium strengthening our bones, and the oxygen filling our lungs were all born in stellar furnaces billions of years ago, during epochs when Earth was still molten rock. All of human civilization, from the first cave paintings to modern space exploration, represents a minuscule fraction of the lifetimes of the stars we've studied, providing profound temporal context for evaluating the relative importance of contemporary events, like observing human history through a temporal telescope that compresses millennia into moments. We recognize that crises dominating today's headlines are brief episodes in a vastly larger narrative. This perspective doesn't diminish the importance of human suffering or achievement, but offers essential balancing context for our anxieties and sense of urgency. As possibly the only form of matter in the local universe capable of contemplating stellar scales with genuine understanding, we carry extraordinary responsibility to preserve and expand this capacity. We are quite literally the universe becoming conscious of itself, representing billions of years of cosmic evolution, culminating in the remarkable capacity for self-reflection. The extinction of human consciousness would mean that trillions of stars would return to existing without any observer capable of contemplating their magnificence, questioning their mysteries, or appreciating their beauty. When we consider the vastness we've explored, we must remember that consciousness, this miraculous ability to understand and appreciate cosmic scales, represents the universe's most remarkable achievement. We are 1.4 kilograms of organized matter that can comprehend objects trillions of times more massive than entire planetary systems. This achievement transcends any individual human accomplishment, representing something so extraordinary it borders on the miraculous. Through us, the cosmos has developed not just awareness, but the capacity for wonder. Detailed knowledge about the structure, evolution, and ultimate destiny of hypergigants doesn't diminish, but rather tremendously amplifies our appreciation of their beauty. Like a musicologist who understands the complex composition underlying a symphony's emotional impact, scientific knowledge reveals layers of elegance completely invisible to casual observers. Betelgeuse, glowing in Orion's shoulder, now carries an epic story of birth, tumultuous youth, and impending death that enriches every telescopic observation and even naked eye glimpse. All human beings, regardless of their culture, nationality, religious beliefs, or personal circumstances, share precisely the same stellar origins and contemplate the same cosmos filled with hypergigants. Like inhabitants of the same small planet orbiting the same ordinary star in a galaxy filled with similar objects, our superficial differences pale dramatically before our shared cosmic heritage. Stellar perspective reveals that we are all descendants of identical nuclear furnaces, all contemplating the same magnificent cosmic spectacle. The telescopes and sophisticated instruments that allowed us to explore distant hypergigants represent dramatic extensions not merely of our limited biological senses, but of human consciousness itself. Like tools that transform fundamental limitations into infinite possibilities, scientific technology demonstrates humanity's unique capacity to transcend the conditions of our biological evolution. Through science, 1.4 kilograms of consciousness can map structures trillions of times more massive than entire planets, reaching across impossible distances to touch the unreachable. This technological amplification of human awareness represents one of evolution's most extraordinary achievements on our planet. We have transformed from primates aware only of immediate surroundings and seasonal changes into beings capable of contemplating the largest structures in the observable universe. Through our instruments, we've extended conscious perception across distances that dwarf galactic dimensions, allowing awareness to touch scales that should be forever beyond biological reach. Knowledge about stellar scales should become the shared heritage of all humanity, not remain the exclusive privilege of scientific specialists. because it offers transformative perspective applicable to virtually every aspect of human life, like a powerful mental tool that permanently expands cognitive capabilities. Education about cosmic scales trains the human mind to deal effectively with the complexity and challenges of our modern world. A child who truly understands the dimensions of Stevenson 2 to 18 develops mental flexibility and perspective that proves applicable to any future problem they might encounter. This democratization of cosmic knowledge represents a quiet revolution in human potential. For the first time in our species' history, anyone with access to basic internet technology can develop profound cosmic perspective that was once available only to professional astronomers. This widespread cosmic literacy may prove essential for humanity's future psychological health and continued growth as a species capable of understanding its true place in an infinite universe. Our journey through stellar scales creates an insatiable appetite for future discoveries, motivating new generations of astronomers, physicists, and curious minds of all types. Like opening a portal to infinite territory filled with mysteries, this cosmic perspective virtually guarantees that the search for knowledge will continue expanding as long as human consciousness exists. Future telescopes will reveal even larger hypergigants, exotic planets orbiting giant stars, and cosmic phenomena we can currently barely imagine. The next generation of space telescopes will peer deeper into cosmic history than ever before, potentially revealing population 3 stars, those primordial giants that may have exceeded even Stevenson 2-18 in sheer size. We may discover stellar structures so extreme they challenge our current understanding of what remains physically possible under known laws. Each new revelation will expand our comprehension of cosmic scales even further, continuing this process of perpetual discovery. Contemplating hypergigants inspires art, music, literature, and cultural expressions that attempt to capture our emotional response to infinity in forms comprehensible to normal human experience. Like artists courageously trying to translate cosmic symphony into accessible terrestrial language, creators develop entirely new ways to express wonder, existential terror, and sublime beauty in the face of incomprehensible vastness. This emerging cosmic art may represent the unique cultural contribution of the first species in cosmic history to truly understand stellar scales. Consider how cosmic perspective has already begun transforming human culture in subtle but profound ways. Contemporary poetry speaks naturally of stellar distances, modern music incorporates cosmic themes and scales, and visual art attempts to capture the sublime beauty of nebulae and hypergigants. This represents the emergence of genuinely cosmic culture, creative expression informed by scientific understanding of scales that dwarf all previous human experience. Understanding stellar scales forces the development of new philosophies that incorporate cosmic vastness into practical human value systems. Like ancient sages who contemplated mathematical infinities but still needed to live meaningful, finite lives, we develop ethical frameworks that acknowledge our physical smallness while celebrating our unique responsibility as conscious observers. Important personal decisions gain entirely new dimensions when considered thoughtfully in the context of billions of years of cosmic time and trillions of stars. These emerging cosmic philosophies may prove psychologically essential for humanity's mental health as we continue expanding our understanding of universal scales. They provide robust frameworks for maintaining meaning, purpose, and emotional stability despite our apparent cosmic insignificance, demonstrating that consciousness itself represents the universe's greatest achievement. After exploring the violence, instability, and ultimate mortality of hypergigants, we develop profound appreciation for the exceptional stability of our sun that made complex life possible on Earth. Like survivors who found sanctuary on a safe island in a perpetually stormy ocean, we recognize that the precise conditions necessary for consciousness evolution remain extraordinarily rare throughout the cosmos. Our fortunate location in the habitable zone of an unusually stable star represents a cosmic lottery victory that should inspire both gratitude and responsibility. The knowledge about stellar scales that our generation has painstakingly developed will be transmitted to future generations, who will undoubtedly expand it far beyond our current understanding. Like cosmic librarians carefully preserving irreplaceable wisdom for our descendants, we participate in an intellectual project that may continue for millions of years. Our great-grandchildren may eventually travel to other star systems, carrying the cosmic perspective we've developed into territories currently unimaginable. Understanding that all the hypergigants we've studied will eventually explode catastrophically or collapse into black holes offers essential balancing perspective on universal impermanence. Like cosmic students of impermanence contemplating transience on truly galactic scales, we learn to appreciate current beauty while gracefully accepting inevitable change. Even mighty Stephenson 2-18 remains temporary, reminding us that excessive attachment to any particular cosmic configuration represents illusion. This acceptance of cosmic impermanence paradoxically makes our temporary existence infinitely more precious rather than less meaningful. Knowing that even the mightiest hypergigants remain ephemeral helps us appreciate the extraordinary rarity and beauty of conscious experience in a universe overwhelmingly dominated by unconscious physical processes. If human consciousness successfully managed to comprehend scales measuring trillions of kilometers, while starting from the modest 1.7-meter perspective of biological evolution, what other seemingly absolute limitations might we eventually transcend? Like proof of concept demonstrating that human minds can dramatically exceed their apparent initial conditions. Our success with stellar scales motivates ambitious attacks on other seemingly impossible problems. Consciousness capable of mapping hypergigants may eventually solve virtually any mystery approached with sufficient persistence and creativity. Our successful journey through currently known scales prepares human minds for future discoveries that may prove even more transformative than hypergigants. Like athletes systematically training for future competitions of unknown difficulty, we expand our mental capacity to deal confidently with revelations we cannot currently imagine. The universe has consistently held surprises for every generation of observers, and our generation is preparing essential mental groundwork for the next revolutions in human understanding. The curiosity that originally led us from familiar Betelgeuse to impossible Stephenson 2-18 represents a fundamental force driving consciousness evolution throughout the universe. Like cosmic energy that mysteriously transforms inert matter into active, questioning observers. Curiosity may represent the cosmos's most important emergent property. Without this driving curiosity, trillions of stars would exist eternally without any conscious being capable of contemplating their magnificence or persistently questioning their mysteries. This curiosity represents biological evolution's greatest triumph, the development of matter genuinely capable of understanding matter, of universe becoming authentically conscious of universe. Through human consciousness, the cosmos has developed eyes capable of seeing itself clearly, minds able to comprehend its own structure, and hearts capable of appreciating its own profound beauty. We reach our final synthesis, the culmination of our cosmic journey. Although we remain microscopically small compared to the scales we've successfully explored, our capacity to understand them demonstrates conclusively that true greatness cannot be measured solely in kilometers, kilograms, or conventional physical dimensions. Like living proof that consciousness transcends all apparent physical limitations, we represent something genuinely extraordinary, atoms organized in precisely the right way to map entire galaxies. Our physical smallness becomes completely irrelevant compared to our infinite capacity to understand, question, and admiringly contemplate the cosmos that both surrounds us and ultimately created us. And that brings us to the end of our journey for today. If you're still awake after all this, I guess the video must really be good if you enjoyed it. I'd truly appreciate it if you could leave a like and subscribe for more videos like this to keep the experience going. Click and watch the next video that's popping up on your screen. I'll see you there. Until next time.